Welcome everybody. Sorry I missed you all last month. I was at a conference. As always, we kind of start off with a few announcements, club news and that sort of thing, so I figured we'd start with that. Next, we've had pretty crappy luck with public nights up to now, which is actually typical luck, I guess you could say. We've not been able to have one. Next one is scheduled for May 17th. That is a date I cannot make because that's graduation. So I have to attend that ceremony and all the nonsense that goes along with it. So I will not be able to make it there, but as always, volunteers are welcome and needed. You know, if the typical string of luck plays out, that will be a very cloudy night, but you know, every once in a while lightning strikes. We hope not literally, but so we may get a good night for that. Next general meeting is May 22nd. And anything else that date wise?
Just pointing out that May 14th is the deadline for the Planetary Society grant. So,
Okay.
So I'd like to get all the information from these contractors as I can. I hope they'll get back to me before then.
Ball's kind of in their court. You want to say anything about the whole ongoing saga?
Well, we were
scope?
just talking about that a little bit. The Planetary Society grant is a grant that's set up for. It's called Shoemaker NEO grant, and it's set up for doing follow-up on NEOs, and for doing characterization of NEOs using different photometric filters, getting some light curves, that sort of thing. So we have the capability of doing that, by the way. We've got it not in this sky, but in clear skies. Let me get this down here. Just to prove I was here.
Okay.
Anyway, we've in the past have gotten 2 NEO grants from Planetary Society. We got one for camera
I'll take the
and
names.
some very expensive filters. All filters are very expensive these days.
Yeah.
So, but the camera was the QHY 600 camera. So, and it has the capability of using GPS to get a very accurate time down to within partial millisecond. So, I mean, it's very, very accurate. Now, there are some other delays in the computer that you have to watch for. But that does a pretty good job. It gets down to within a millisecond or 2 maybe. That's where I would put that. Regardless of that, that's pretty accurate. So when we get a fast moving NEO in there, we can really get a good time if we get a good position. Anyway, that was one of the grants. The other grant was when we decided we were going to remotely operate Parkway, and they set us up with a grant to buy everything we needed to buy to make Russ the victim of putting it all together. So those are the 2 grants that we've gotten from them so far. I've gotten a personal one from them in 2013. So it's not like we don't have cred. We've got a lot of cred. We've got a lot of information on. I sent you that list of stuff. Most of it's not made up. Anyway, we've got a lot of work done at Parkway, and we've got a reputation. Some of it's not even bad. Anyway, I'm going to try to get this done, but my problem is I don't know how I'm going to approach it, except that I think I'm going to go with getting the landscaping done, getting the foundation poured, getting the concrete floor done, doing the gravel apron around it, and a 6-foot high fence around that. And that's going to be my goal to have the Planetary Society cover all that. Now, the problem with this is, it's all preliminary. Everything that we're doing here is gonna depend on getting more sources of funding down the road. So we're going to the Planetary Society, hey, can you get us started here? I don't know if they'll buy that or not. We'll see.
And we've had, what, 2 meetings now of the relocation committee, which Russ is the chair on, talking about stuff like that. So it's, you know, we hope part of a larger plan
Yeah.
of sorts. Anyway, anything else? Oh, we do have one announcement, which is Tony, who you know, will be stepping down as the treasurer. So we're going to need a treasurer. I asked for volunteers, I guess. The treasurer is an appointed position and kind of sits on the board and does what treasurers do, keeps track of all the money, basically, pays the bills, that sort of thing. We would like to get somebody in there pretty quick because Tony, I think sounds as if he is kind of pursuing another opportunity of some sort and wants to get out from under treasuring.
He is jumping at the bit.
Yes.
Yeah, he's wanting to get out.
So, anybody wants to volunteer to be a treasurer? Tony, I think, will assist in the transition, so you can, if you would like to do it and would like to step up to that, we need help. And if you have an idea, if you have somebody that you want to push forward, well, we will need to fill that position. Anybody want to volunteer?
Sure, what the hell.
He finally broke.
All right, thank you.
All right, excellent. Well, thank you. And you can, I guess you and Tony can get together and work out all the details and all that. But that's great. Thank you so much, because yes,
That's conditional on getting my t-shirt.
that must be. It's definitely the most powerful. If you go by the golden rule, the most powerful person in the club is going to be the treasurer. So anyway. All right, a couple of other things. I saw this. Can we turn off the lights, maybe at least a few of them back there, so we see the screen a little bit better? I don't know if they replaced the lights in here, or my eyes are just getting more sensitive to light. But anyway, so you've probably seen this, but just in case you haven't, there's this opportunity to, they referred to it in something as the Planet Parade, in something I read the other day, and I thought, it's not much of a parade. There's 2 and possibly 3 planets here, depending on how patient you're willing to be. But they were talking about this smiley face thing. I think Jan actually sent around a news item about that. So this is, scheduled for tonight, I guess, or not scheduled, but will occur tomorrow morning. What you're most likely to see is this, if you decide to go out and try to catch this. But, on the off chance that maybe
There's a few breaks there.
you think this is optimistic?
That is optimistic.
Okay, well.
That's not a recurring thing every year, is it?
I don't know. No.
Not on a yearly basis.
Doug, it's my understanding that you're gonna be out and call us if the sky's open.
I think I would call that your misunderstanding. But, I may have one of those nights where I can't sleep, in which case I still am not going to do it, but I'll be awake while I'm not doing it. Okay, so yeah, that's one thing I wanted to just point out. Another thing, I don't know if any of you saw this, but the Mid-States Astro League meeting they've announced the registration is now open, so this is sometime in June 13th. Through the 15th, it's at the University of Arkansas Little Rock this year, so if you would like to attend that, you probably need to start getting your registration done pretty soon. We've had people talk at this before. Give a presentation. I know Gary has. I think last year, Murat Rato, who's one of our sponsors, I think was a feature speaker. So anyway, so if you want to attend this, happening at a time when I can't make it, but if you would like to attend, this is an opportunity. Okay, that's about all I have for announcement. Anything else? Good of the club? Anything on your mind? Okay, well, so what I've done with these meetings, which again, you know, if you got ideas on stuff, just by all means let me know. You know, I do like to make these things as interesting for you as I can. But one of the things I've tried to do is sort of have a little presentation on some constellation or something of interest in the sky that's a little more of a general presentation, and then followed by kind of a longer, more topic specific kind of thing. So I was thinking about what to do on this, and it kind of occurred to me as I was looking through all the past presentations that, you know, I'm kind of running out of constellations. And I was thinking about this, and, you know, one of the things that Laura and I like to do with, you know, being the exciting people that we are, is we usually pick some TV show to watch in the evening. And one of the TV shows we've been watching in the evening is this. Has have any of you seen this? Mm-hmm. This is a show that are dramatizations of, if you've heard of Tony Hellerman, he's a writer that kind of specializes in writing about the Southwest, right? And his main characters are, oh, there's Tony, hey, and the T-shirts. We have a volunteer, by the way. Well, so.
But he won't actually volunteer unless you give him a shirt.
I can do that.
Okay. Well, anyway, so these are dramatizations of these novels. This writer who writes about his characters are Navajo police officers, basically, and they're pretty cool. Anybody read any of these? They're interesting books, basically. And so, you know, I've been watching these stories, and I love the Southwest, and particularly the Four Corners. If I could live anywhere, I probably would live right there. But so, you know, it's a very compelling landscape for me. And, you know, I watch these shows and you see these beautiful clear skies. They're always clear. And, you know, anyway, so I thought, what about doing a little presentation on a different, you know, the kind of sky from a different cultural perspective, right? You know, we've listened to so many of the stories of the current constellations, which are mostly, you know, most of their mythology is rooted in kind of Greek and Roman myths. And, you know, as we've pointed out a number of times, the Greek and Roman gods are a poorly behaved lot. They tend to do all kinds of horrible things. So a lot of times it's stories about, you know, awful behavior. And why not look at somebody else? So what I kind of settled on was essentially just a little bit about the kind of Navajo astronomy. And they don't, it's not quite as central to their ethos as some of these astronomical stories are in some other cultures, but they've got some pretty interesting ones. So there's a whole kind of cosmology basically with this, as you can probably imagine. What I was going to kind of focus on here was, and again, these are words that, you know, and again, you probably know this, but Navajo is a very complicated spoken language to the point where it has been used in the past as history as code without any translation, right? You know, if you've ever heard of the code talkers, right? So I will probably butcher some of these pronunciations here, but I also kind of thought about this because I have a friend who's was a teacher on the reservation on Navajo Man. His son guided me back to some backcountry sites one time, and so I kind of got to know him a little bit. So I thought maybe this would be kind of a little homage to that as well. But this word right here, Nahokas, means that which rotates, or something like that. And it refers to this grouping of stars, some, you know, sure, obviously now, or at least in our kind of current mapping of the sky, referred to differently, but they center around Polaris. They center around the North Star. So, and they are treated, even though they're kind of separate, they're sort of treated as a unit, basically, which is how they come to have this name. And that's pretty typical of the kind of Navajo astronomy. They tend to pair their constellations. So, just a little bit of background. Again, I don't know, anybody ever travel through this part of the country? This is just a strikingly beautiful place, in my opinion. This is Navajo Reservation. occupies parts of 3 states, New Mexico, most of it's in Arizona, New Mexico, Utah, and in Arizona. It's really huge. If the Navajo Reservation were a state, it would be, I believe, the 40th largest state if there were 51, right? If it was added to the list, so it's very, very large.
Does that include Canada?
Not including Canada. No, that would make it 42, right? 41. Canada would be number 1, which I think those people talking about annexing Canada really wouldn't want to, but that's a whole different topic of conversation. But anyway, and so it's a relatively kind of sparsely populated area. The total population of the Navajo Nation is probably under 100,000, so it's a fairly sparsely populated. It's actually interspersed with another reservation right here. This is Hopi Hasatsanom. So
Hopi?
Hopi, yeah, Hasatsanom. So they live in this kind of uneasy relationship, which is interesting. I was traveling in this area one time. I picked up a hitchhiker who was headed to the Third Mesa. It's one of the kind of Pueblo type structures that they live in. It was really cool because I had this guy with me, and so he said, come and meet my family. And so I got to go to a part of that normally, white folks don't get to go to, and it was a really interesting experience. But anyway, so like I said, this is a place I really kind of very fond of, and it's a culture I don't claim to know much of anything of importance about, but interesting in my opinion combination of kind of very traditional lifeways and not so traditional ones. I guess you could say it's an economy that's largely based on herding, sheep herding and goat herding, a little bit of agricultural kind of things, hunting, that sort of thing. As I said, they kind of live in this style. It's a little bit of a mix of the very ancient and the very modern. These structures you can see here are kind of the sort of traditional home, the Hogan, which is a kind of a traditional home. They have a astronomical alignment. The door always kind of points in the same direction and stuff. So anyway, and like many cultures, they have a tradition of stories about the sky, right? And their creation story, which is actually pretty similar in a lot of ways to a lot of others, involves the sky. It's this kind of the father of the sky and the mother earth. They're usually depicted this way in kind of traditional depictions with their legs always kind of crossing one another, which indicates the kind of interaction of these things. So anyway, the universe view here is, as I said, kind of composed of constellations that are a lot of times similar stars to some of the groupings that we do now, but very different kinds of stories about them. And it all radiates out from the North Star, radiates out from Polaris. So that's the kind of where I want to at least focus in a little bit. So this little grouping right here is are the ones I want to kind of talk a little bit about. There are stories about all of these, right? Notice that they kind of come in pairs. It's part of their kind of sky belief. But the stars that kind of form these constellations are, again, similar and encompass some of the same ones. So if you look up to the North Star here, for most of us, it kind of has that, there it is right there. That's the North Star is the North Star, right? Because the Earth's rotational axis is almost pointing at it, right? So it pivots around. That's why these group of constellations is kind of referred to as like the revolving ones or the rotating ones or something like that, because it reflects the fact that they rotate in sort of a couple of different ways. There's that movement around the North Star, but then there's also kind of the attitudinal change as they go too, and that name that they attach to these reflects that. So I took this little image right here from whatever, Stellarium, I guess, the little planetarium program, and it includes, and the constellations we're going to look at include parts of the Great Bear and parts of Cassiopeia that are incorporated into these. So here it is. I didn't realize that you could do this until I started fiddling around with Stellarium, but it'll show other constellation groupings, you know. And so here are the Navajo ones, right? So there's Polaris right there, and then you have, as I said, they're called. That name means the revolving ones, the rotating ones, or something like that. So the names translate to be roughly the rotating male and the rotating female, which are really fairly descriptive, but not very poetic names, I guess. There's a bit of more of a implication to it than that, though. And so here's some of the other ones as well, but I wanted to kind of just look at this grouping that is around Polaris. So again, here's all those somewhat difficult for me anyway words to pronounce. But there are kind of three parts to this. There's Nahokispico, which is means something like the hearth fire or the central fire or something like that. And it in the ethos it represents the Hogan. It represents the fire that's in the center of these kind of traditional sort of structures that they build, in many cases still live in at least part of the year. And then the two, occupying figures in this are Nahokispikai, the rotating male, and Nahokispiata, which is the rotating female. So here's the central fire, right? And in the stories and in the kind of mythos, it represents the Hogan itself. So it kind of represents the ancestral home of the people, essentially. Kind of represents all the things that they sort of associate, which I suppose pretty much anybody associates with home. Eternal light, safety, comfort. Also, just sort of human consciousness in general. So the North Star kind of in their view represents all that sort of thing. And then the other thing it does is it serves as a uniter to the two other constellations that form this group. So in a sense, it's kind of this family idea. So here's Vika, the male rotating one, formed mostly or from many of the stars, the asterism of the Big Dipper, right? Typically presented, there's kind of how it is depicted sometimes, typically presented this way as a warrior figure, but not more a warrior figure that represents protection and physical protection, but also spiritual protection. It's typically depicted with a hunting bow and arrow, and it kind of represents the protective component of the family and the spiritual protective component. Complementary figure then is the female rotating one, which includes parts of the stars of Cassiopeia. And I don't know if it's a coincidence or anything, but it's interesting that in this set of star stories, it's a female figure, and in the kind of Greek Roman derived ones that we kind of think about now, also a female figure, right? Cassiopeia was a queen, not as nearly a respectable figure in my opinion as this one, but still a female figure. So depicted as holding objects as the male is, but in this case the objects that are being held are cooking utensils, grindstone, which that's pretty central because corn is a major part of the diet here, so they grind that corn up. And stirring sticks, those still used. There's kind of a particular kind of stick that's used to stir the food. So it kind of represents, provision for the family, basically. So these are kind of complementary characters. The other thing that really is represented by this is growth and excuse me, growth and stability, but also harmony, and that's a very important concept in the culture. The idea of harmony and living in harmony is a major kind of life way associated with these. So these are the kind of the center, literally and kind of conceptually, sort of the center of the Navajo cosmology. One of the things I liked about these stories, by the way, you read, often in preparing the presentations, I dig out an old mythology book that I have, or look at stuff online, and I read these stories about horrible behavior of the gods, right? Doing just awful things that you can't even imagine. I really like the fact that these, the characteristics of them are harmony and protection and family ties and that sort of thing. So it's kind of refreshing after reading about gods that basically send their own children off to be killed by monsters. So anyway, I kind of liked that. So it was a little refreshing. As far as interesting stuff that you would find in these constellations, I think probably one of the most interesting objects, and maybe most important ones, is Polaris itself, right? Polaris is a brightest star in Ursa Minor, Alpha Minor Ursae. It's actually a triplet. It's a 3-part star, but the A element of it, the brightest one, is a variable star. It's what's called a Cepheid variable, and Cepheid variables are important for a number of reasons. Kind of fundamental to understanding the way stars work. If you remember your HR diagram, your Hertzsprung-Russell diagram, they fall off the kind of main sequence here. They're relatively large stars, but they vary in brightness by just physically getting larger and smaller. They blow up and then shrink down, or blow up and shrink down. And what causes that is this complex pattern of ionization of the gases that are inside the star that traps radiation, and that spans it, and then they de-ionize as that happens, and they contract back down. And the thing that kind of characterizes them, they have this sort of characteristic shape. I mean, I took a class in variable stars from the AAVSO, and so I learned about all this stuff. It's kind of a steep rise to the maximum, and then a little bit of a more gradual fall off, and then a steep rise. But it's a very regular, a very regular period that it varies on. And the reason why that's important, at least one of the reasons why that's important, this is actually the pattern for Polaris, so you can see it varies on a time scale. And you can actually kind of see this if you go out and look at Polaris, on a night-by-night basis. It does actually look like it's getting brighter and dimmer. One of the things that's kind of important about that is that it helps to, Cepheid variables are important parts of the cosmic distance scale, and they're what are called standard candles. So, obviously if you're going to try to measure the brightness of something, you have to know, in order to know intrinsically how bright it is, you kind of have to know either how far, you have to know its actual brightness, not just its, distance, right? So a dim thing up close can be as bright as a bright thing far away. What Cepheid variables do is they have this very regular relationship between the period, the amount of time it takes to go through those cycles of bright and dark and bright and dark, and its luminosity, its intrinsic brightness. So if you can measure the period of a Cepheid variable and its apparent brightness, you can work your way back to its actual luminosity, and then you can tell how far away it is. You can really tell because you can use inverse square law of radiation to figure that out. So they form, again, what are called standard candles, and they actually fill in a pretty big gap of the cosmic distance scale. Things that are within maybe about 100, 80 to 100 light years, which a hell of a long way, but close on the cosmic scale. You can use parallax. You can kind of measure their apparent change against the background and figure a little trigonometry and figure out how far away they are. But once things get too far away, they don't move far enough against the background to really be accurately measured. So then you have to move on to something else, and a big piece of that time scale is filled in by Cepheid variables. That's actually one of the reasons why we know how far away things like nearby galaxies are, because you can actually see Cepheid variables in like the Andromeda galaxy, and that provides a very accurate way of measuring the distance, and then you can use that, you could use things about that galaxy, the relationship between how fast it rotates that's another standard candle, and that gets you even further out. So a lot of the, a major part of the cosmic distance scale, so almost all of cosmology basically depends, observational cosmology at some points depends on knowing these kinds of things. So just a super important part of these distance scales. A couple of other things that are kind of interesting. This is the middle of the handle of the dipper, Mizar and Alcor. This is used in the ancient world, and maybe even now, as a test of your eyesight. Keen eyesight was if you could tell them apart, if you could actually see, these are visual double, right? You can actually, if you can actually see the separation between them, then you were considered to have reasonably good eyesight. I probably could when I was, about 18 and living at high altitude, so there wasn't a whole lot of atmosphere in the way. But it's not even close. I'm lucky if I can see them stars at all. But anyway, so this was considered an eye test. Other things, a couple of my favorite galaxies are in the in this general area. This is one I've always really liked, M51, the Whirlpool, kind of one of my personal favorites. Pinwheel, another one that I like a lot. This is one, Parker, should look familiar. You got this one the other night, didn't you?
Yeah, with a 50mm lens.
And I was amazed by how, that you could still see the bar and a little bit of the arm structure and stuff.
If you look closely at that image, you can see other little galaxies.
Which is actually a precursor to what I want to talk about next. But anyway, this is the Owl M97. Apparently, this one's, I don't know, Russ, have you ever shot this one? Apparently it's really hard to get. Like it's kind of dim and...
It is dim.
That's not that bad.
Is that? I don't know. This is, again...
It's pretty easy.
Picked it up with the C star.
Yeah, okay. Well, maybe you shouldn't believe everything you read. There's a little galaxy.
It's hard visually.
Yeah, there's a galaxy right there. Anyway, there's another one right there. Then another kind of pretty sort of binocular object that looks really pretty in binoculars is this Carolyn's Rose. Carolyn in this case is Carolyn Herschel, the sister of William Herschel, who we talked about a little while back, one of the most prolific discoverers of comets, but also a mapper of the sky, and she mapped this object, or it was named after her. Anyway, so that's a little bit about some cosmic traditions other than our own, or I guess other than the Greek-Roman one that we kind of think of as ours. Questions? Anything?
Do the Chinese have their own, ancient Chinese?
Yeah, they
culture
do.
have their own?
Definitely, and in fact, one of the things I was going to try to do, and this was my original plan for this meeting, but was to kind of do a presentation on various sky mythologies. The problem is, it was too much. I couldn't. I'm going to need much more time to put something together, because this is just, every cultural tradition has something associated with it, and you have to pick and choose what to talk about.
But what's amazing is that some of the constellations are the same creature across those, like the dragon.
Yeah, and that sort of implies either a lot of really, really interesting coincidences, or that there was a lot more kind of interconnection in the ancient world than we apperhaps think about. I was very struck by it. And in some myths, the same myth, same story appears in different, different names. The characters have different names, or whatever. But it's essentially the same story, and so I always found that kind of interesting. Okay. Okay, so the other thing I wanted to talk a bit about, this is what I came up with because I couldn't put together a presentation on myth in time. And we talk a lot about small solar system bodies, and we've kind of had a lot of attention to that in the club. And I just wanted to kind of talk a little bit more about the general background of these. So this particular presentation really kind of came from that, and from some of the discussions we've been having about moving telescopes and the importance of them and all that. So I wanted to just talk a little bit about why what small solar system bodies are and why they're important and what the significance of them was. So you can kind of tell that they've had a little bit of a mixed reputation in the astronomical world that at times have been referred to as the vermin of the skies, right? Because they got in the way of trying to look at the more interesting things that would streak up people's pictures and all that sort of thing. I'm always kind of interested in that and wanted to sort of delve into it a little bit. And you actually kind of at least I started running really quickly into the history basically of astronomy as a science. And for a very long time, astronomy as a science was really about mapping and cataloging and measuring motion, right? It wasn't so much a concern what all those things out there were. It was more like where were they and how do they move and all that. And it led to some pretty sophisticated thinking. Some of the finest mathematical minds of history have largely devoted themselves to understanding things like planetary motion and that sort of thing. So, the cutting edge of astronomy science, maybe in the 1800s or so, that's kind of where it was. These are the Herschels, right? They were cataloging things, right? This is supposed to be, I reminded myself of Laplace, French mathematician, who was one of the, in addition to the inventor of a lot of math stuff that you learn about in classes, was interested in celestial motion, right? And they didn't really care that much about, let's see, that's incorrect to say that, but the emphasis really wasn't on where what the things actually were. And at that time, there was a pretty keen interest in the solar system, right? Because the solar system was full of stuff that was obviously moving around. So a lot of what's understood about things like laws of gravity and that sort of thing came about largely, at least in part, by looking at motion, and particularly motion of the solar system. But as astronomy kind of developed as a science, it started to change. It started to kind of diverge a little bit. There was sort of traditional astronomy, which still exists, right? But there was sort of an increasing emphasis on astrophysics and cosmology, right? Astrophysics would be not worried so much about where the things were or how they move or all that sort of thing, but more like what their physical properties were and how they work, basically. And then cosmology would be just the study of the entire universe as a whole. And cutting edge work in these sciences kind of shifted towards this sort of thing. Became much more interested in trying to understand all that stuff that was very large and very old and very far away, and essentially composition of the universe as a whole. And to the point where kind of traditional solar system astronomy got lost in the shuffle a little bit. A lot of the technology that went into improving astronomical instrumentation was largely about trying to look farther and further back in time, right? So, the Hale telescope was built largely to try to understand the structure of the universe. The Hubble Space Telescope was largely built to define the Hubble constant, right? How fast the universe is expanding. That was one of its major purposes. The Webb telescope is designed to look at things very, very far back in time, right? That's why it sees things at very long wavelengths, because it's looking at things that are intensely redshifted, very, very, very far away, and therefore very old. And the new generation of Earth-based telescopes also kind of designed largely for those sorts of things. And it sort of left the solar system as kind of an orphan in a way. I don't know, anybody ever read this book? You have read this book?
I have.
Yeah, this is a really good book.
It is.
It's quite dated by now. I think it was written probably in about the mid-'80s, I guess. But it talks about some familiar people. It talks about astronomers at Palomar who are trying to look at where quasars started, right? Quasars are thought to be kind of galaxies when they're babies. And so they're trying to look very far back in time. And then the writer here also follows the Shoemakers, right? The namesakes of the grant that Gary was talking about earlier, who are interested in looking at solar system objects. But it has this wonderful quote in it that, you know, to many astronomers he's talking about here, these are people he's talking about at Caltech, so these are, you know, kind of the cream of the crop, basically. The solar system was boring, right? 9 balls of 9, because this was back before it became 8, right? 9 balls of non-luminescent matter whirling around a pathetically normal star, in addition to some gritty stuff. The $2 this is the line that stuck in my head, the $2 table in the great casino of the sky. And this was how a lot of astronomers kind of looked upon the solar system. It was kind of the, you know, the deadest game in town, basically. I like the line about gritty stuff here, because that's what I want to focus on here a little bit. And it doesn't mean that was a universal amongst all of them. Probably the most famous astronomer of the last century, and probably this one as well, was a planetary astronomer, Carl Sagan. He did a lot of his work on studying Venus, basically. He was certainly still pretty intensely interested in the solar system. But a lot of the people that started kind of taking up the mantle, a lot of the scientists that started taking up the mantle were mostly like geophysicists and things like that, people whose training was not really in astronomy or astrophysics or any of those sorts of things. So these are the Shoemakers, right? Both, I believe, passed away now, but
Yes.
Carolyn not that long ago.
A couple of years ago.
Yeah, but and these are of course the namesake of the grants, but they embarked on a project to try to map, and this was, you know, back before CCDs and things like that. So they're using film to do this, to map out the, you know, objects, small bodies in the solar system. Of course, one of the, again, I don't want to imply that the solar system became a place where no science got done. In a lot of cases, it was pretty cutting edge stuff. It was probes and things of that nature. So there was a lot of exploration, both in person in the case of one solar system object, that one right there, and by proxy for a lot of others. So there was certainly, you know, a lot of science being done, but again, a lot of it was not being done by astronomers. Any of you have ever seen there was a series on HBO some years back called From the Earth to the Moon, and anybody ever watched that? It's about the Apollo missions. And my favorite episode is the one where the geologist takes the crew out and, you know, tries to teach them about geology. But it was a geologist, right? It was not somebody you might think of as an astronomer or an astrophysicist. That all kind of started to change, though, I think, when a couple things started happening. First of all, that all these probes started to reveal that, you know, really interesting stuff going on out there. The planets were not as dead as, you know, it might be led to believe, and other objects not so dead either. That was part of it. Other things that began happening, the improvements of technology, got easier to observe things, right? So telescopes that, you know, nobody wanted to waste a big telescope looking at some, you know, rock in the sky, but if you had good technology, you could get similar sort of data with basically digital camera technology with much smaller instruments. So there became more of a capability to observe these things. And then the other thing was discovery of other solar systems, right? Other planetary systems. So comparative planetology became a more of a thing, you know, trying to understand how solar systems kind of came into existence. And so interest in the planets increased, but also interest in things that are not planets, small solar system bodies. You know, I think people kind of realized this all along, but it became more apparent that if you wanted to understand how a solar system like ours came to be, the best clues were probably some of the stuff that was left over from making it. So a lot of these small solar system bodies were just pieces of, you know, construction material that were left over from the formation of the larger, more apparent bodies. So that's kind of a long introduction, but that's why I kind of wanted to talk a bit about these small solar system bodies. My original plan was to talk about all of these things, you know, compare main belt and near Earth objects, comets, Kuiper belt objects, all the trans-Neptunian objects out here. I quickly realized that's way too much to talk about in an hour or 45 minutes or whatever amount of time people will actually listen to me. So I've kind of, what I'm planning on doing is breaking this down, right? So tonight I want to talk about the rocky stuff, and then sometime in an upcoming meeting we'll look at the icy stuff, basically. So that's kind of a long and probably tedious introduction, but that's what I want to talk about. All right, so what is an asteroid? It's actually kind of a bad name, right? Asteroid means like looks like a star or something like that, and they were named that by the original discoverers back in the 1800s. They look like stars, right? They look like little points of light. They're not really big enough to resolve with very much detail. But basically what an asteroid is, it's an object orbiting, solar system object orbiting the sun that's not a planet or a dwarf planet. And you had to kind of at one point amend that definition because now we have dwarf planets, right? At one time it was just something orbiting the sun that's not a planet, but a rocky something. That's a very important thing to add there. So that's essentially what an asteroid is. The very first one was discovered, which is not an asteroid now. You know, it gets kind of confusing after a while. The very first thing that was called an asteroid was actually discovered on the very first day of the 19th century, January 1st, 1801, by Giuseppe Piazzi, who I believe was a clergyman. He used to point his telescope out the window of his dormitory where we lived, and he discovered Ceres. Ceres is also the largest. It's actually now considered a dwarf planet, which means that its gravity is enough to make a ball, right? That's kind of the definitional division now between with asteroids, which tend to have weird irregular shapes, and dwarf planets, which are balls, or spheres, roughly spheres. Anyway, and of course, a lot of the larger asteroids were discovered in the 1800s. And again, this is kind of at the time that they were beginning to find these things, these were considered to be really valuable objects of study. You know, they in the case of some of these, they're actually considered planets. For a while there was like 16 planets, most of which now are considered to be minor planets, right? Something other than a dwarf planet or a planet. So this is the list of the largest ones, and you can kind of see some of them are pretty good size. Ceres is almost 1,000 kilometers in diameter, and so on. Of course, it's not an asteroid anymore. This is a little bit of a dated table. You also kind of get an idea where they are by looking at this semi-major axis here, and that actually kind of plays into the story. You also get a little bit of a sense of what they're made out of by looking over here. And that also plays into the story a little bit. Discovery of, study of asteroids, like I said, was considered to be a really legitimate part of the astronomical field. So there was always a steady beat of discoveries through time. And then later on, when we had automated searches and dedicated searches and instruments with more capability to gather light, the number of these things really sort of took off. So lots and lots of these things have been discovered since then. So one of the kind of defining characteristics of asteroids is kind of where they are. And most of them are found in one of, I won't say one of two places, but in one of two configurations, right? So there's what's called the main belt of asteroids. They lie between Mars and Jupiter. So you can see all the white ones there. Those are main belts. And then you also get what are called Trojan asteroids, which actually are found, they go by a bunch of different names, but they are often found, they're now found in association. Originally, Trojan asteroids were associated with Jupiter, right? And they were in gravitational dead spots around Jupiter. There are these things called Lagrangian points, which are places where the gravitation kind of forms a dead spot, basically. So they would sort of gather in there, be collected in there. So they were they were collectively called the Trojans. There was actually two clouds, the Trojans and the Greeks, but they were collectively referred to as Trojans. Those names are not accidents, by the way. They were intentionally named because the Greeks and the Trojans fought the Trojan War, so they originally named a lot of these objects after characters from the Trojan
And I will
Wars.
tell you, there's not very many characters left anymore that can be applied to these,
No, they have,
because they've used basically everything that was written.
yeah, they have scraped the barrel for, you know, it's like,
I tried to get some of the ones that we discovered, I tried to get them named, and I couldn't come up with anything.
yeah, well, at this point, you're like, you know, guy that was in the front row carrying a spear, you know, what's
Yeah.
his name? 'Cause
Yeah.
we're down to.
Yeah, right.
But,
Or the horseman that took care of the horse.
Yeah, yeah. The kid that carried the flag, you know, let's
Yes,
get
right.
him in there. But anyway, and actually the Greeks and the Trojans were what in the First Light book, that's what the shoemakers were looking for. They were
Mhm.
trying to map this part of it. And actually it turns out there are also essentially Greek Trojan type asteroids around a lot of the planets, you know, which is no big surprise because gravity works how gravity works, right? But these are still the ones that are kind of. The other thing about this is that these are not, you know, there are no barriers between these. There's a lot of dynamics in all this. And I kind of want to get into that a little bit, but
They're transitory items too, coming from one place to the other.
and there's also non-family asteroids, the ones that are sort of drifting around out there, you know,
Yeah.
maybe on their way from some place to another. One of the things that's kind of interesting about the discovery of objects in what is now called the main belt had to do with an idea about how solar systems form, and particularly how planets are spaced. All right. So there's this thing called the Titius-Bode law, which is a relationship, pretty simple relationship that relates the period of a star to the semi-major axis of its orbit. Right. So if you think about an orbit, right, the major axes are the longest and shortest distance that the object. So a perfectly circular one has its major and minor axes are the same length. So this is a shorthand way of thinking about how far away something is when it's as far away as it ever gets. And what they found was that there's this, if you just work it out as a dynamics problem, it follows a relatively simple relationship, and all the planets sort of fall in line, except there's a gap. There's a gap between Mars and Jupiter. There should be a planet there. And so this law actually predated the discovery of some of the objects in the asteroid belt, in the main belt. And people were very happy about that because I thought, oh, this law is vindicated, right? It was kind of a crisis in the study of the dynamics out here because there was nothing there for a while, and then all of a sudden there was. The problem is that if you take all the stuff in the main belt and probably in all the others as well and squeeze it together and make a planet, it's not nearly massive enough to have to play the role it needs to play for this to actually work. So this sort of implies that this is probably this Bode's law, which is based on what's called dynamic relaxation, right? It probably does apply, but other things are going on there, which we'll get to that here in just a second. But anyway, this sort of was at the time it was considered to be often important discoveries because of that. The other thing about asteroid belts is, again, they're not as dense as you sometimes think they are. I mean, there's this idea, right, that if you travel through the asteroid belt, then you're going to be dodging. This is actually a still from one of the Star Wars movies. I don't know if you remember this, but they're going, I don't know, somewhere, and they're dodging their way through all these rocks and stuff. And, in reality, if you pass through the densest part of the main belt, you probably wouldn't see any of these things. You may run across one of them if you're lucky. They're very sparsely spaced.
I read that the average distance is something like 600,000 miles.
Yeah, which is what, 2.5 times the distance from the Earth to the Moon. So they're not too densely packed out there. But again, that kind of provides some clues about how the asteroid belt kind of came to be. Of course, the other thing about the more intensive study of these is that it has come to be found that they're not all the same, right? And not that anyone would ever have expected them to be, but they fall into some particular types. So there's a bunch of groups of these. I mean, if you look at these papers about this, they can be very, very complicated. But basically, they fall into three classes. There's the carbonaceous type, the C type. There's silicate types, and then there's the metallic ones. And each one of these implies something a little bit different about how they came to be, but also, by extension, maybe how the solar system came to be. So the composition of these has become a major topic of interest, largely because of that. So the most common type are what are called carbonaceous types. About 75% of all the asteroids. They're fairly metal poor. They don't have a whole lot of metals in them. What they are made out of, primarily carbon, which is why they're called carbonaceous, but their elemental composition is actually pretty close to the sun if you take out all the volatiles. So they are made essentially of the same things what the sun is made of. And that's a pretty big clue to how the sun came to be, right? The theory is that there was this big disk of stuff out there, actually probably more like a ball of stuff out there, that started to coalesce, kind of get packed together, and as it became denser and denser, eventually it reached a threshold where nuclear processes could start, and you basically get a star. And we can actually kind of see things like that happening now, so it's pretty clear that that's kind of the origin story of stars. One of the other things that's kind of significant about carbonaceous ones is they're little altered by heating. Right? They have not ever been melted. In fact, one of the reasons we know about these things is because a lot of meteorites, things that land on Earth, have their origin as part of a C-type one. So any carbonaceous chondrite or achondrite meteorite are pieces of one of these things that made it to Earth. And if you look at those, the ones that are chondrites that have the little particles of what's essentially primordial material, right? That was the original stuff that the solar system was. You can kind of analyze it and, number one, figure out how old it is, but also what it's made out of. And the elemental composition of those things is, again, very similar to the sun. And that's a pretty big clue about this. They also tend to be in the outer main belt. So if you kind of think about the main belt as having a trajectory of ages, trajectory of compositions. These are the ones that are furthest away, and that's also part of the story as well. So stony types are kind of a mix. They're some of the same components, some of the same elements as the carbonaceous types, but also a lot of silicates and metals. So a lot of nickel and iron in this, and that's kind of significant because nickel on Earth is not very common and usually found rather deep in the mostly rather deep down in the Earth's crust. These are similar to the stony meteorites that you are recovered, but also these are mostly found in the inner asteroid belt. So these are ones that are a little closer, and they also are more likely to be altered, to have been melted at one time or altered somehow by heating. And then the last type is the N type, the metal rich. These are the least common ones. They're mostly made out of metals, nickel and iron for the most part, with some stone in there. And again, these are also typically interior main belt ones. These are almost certainly formed in differentiated planetary bodies. So you have to divide these up into primitive types, which have never been altered. They've never been melted, basically. They are literally primordial material, with some that at one time were probably part of a large enough protoplanet or planetoid or some kind of a larger body that was large enough to have internal melting, right? That the gravity of it was sufficient to squeeze it enough to melt the inside, basically. And if that happens, you get differentiation. The metals, the heavier components, will sink down. This is just like what happens here on Earth, right? The reason why the core of the Earth is iron is that at one time when the Earth was all molten material, the heavy stuff sinks down to the bottom, the lighter stuff comes up to the top, and you end up with this differentiation of the body. So these would have been like the cores of some of those planets. Also one of the reasons why they're relatively rare, because there probably weren't that many of these sort of protoplanetoids, right? These larger objects. So here's the difference between these primitive and differentiated ones. In a differentiated asteroid or planet, you had enough heating to kind of form these layers, so you had a core down. And there are some that are like ones like Ceres, almost certainly differentiated. If you could drill down, land on Ceres and drill your way down into it, you would probably find a molten iron core down there. And then the undifferentiated ones, which are again more primitive type, more composed of less altered material. And these are the ones that carry a lot of information about what the early solar system, at least its chemical composition, would have been like. And again, one of the reasons why we, and I'm using the royal we here, the human race knows this stuff, is recovery. Some of it is actually now we've actually sent probes and things to these, and you can tell a lot about what they're made out of by looking at how they move, right? It tells you something about their density and that sort of thing. But a lot of it is from material that's literally landed on Earth, asteroids. So if you think about it, where these kind of things from, the kind of stony meteorites, the chondrites, they're probably material that was never differentiated. They're a piece of some primitive rock out there that broke off and came through the atmosphere. Some of the other ones like irons and pallasites and achondrite stonies, they were part of a differentiated mass at one time. So iron meteorites, which are I think the coolest ones because they have that weird sort of regmaglyph stuff on those things that like thumbprints all over it. This would have been the type of meteorite that made Meteor Crater, for example, in Arizona. Pallasites, which are probably the most interesting ones, were on the boundary between the core and the mantle, so they contain characteristic pieces of both of those things. Probably one of the most famous meteorites ever found was the crap, I'm blanking on the name.
Greensburg.
The
Greensburg.
Greensburg.
That one.
Yeah. Shoot, now I'm sorry, I'm having a moment. But it's a palisite, right?
Yes.
If you cut these things and polish them, they're absolutely beautiful.
I have a couple of them.
Do you have? I think I saw one once. Yeah.
Yeah.
They're it's kind of a matrix of iron with these little green periodites. These little,
It's a big mix of
yeah,
stuff.
yeah. Yeah, they're really striking looking things. And then the achondritic stonies, they're achondritic because the chondrules, those little pieces of stuff, got melted away, right? But the stony bit is still there, and they were probably from the outer mantle and crust of these things. So one of the major reasons why we kind of know about these things. So here's a little bit about that. I always like to take an opportunity to talk about meteorites because they really fascinate me in any number of ways. Okay, so that's kind of a little bit about what these things are and what they're made out of. And I hope kind of hints at how they came to be and largely how the solar system came to be and how they provided information and clues on that. One other clue to all this is that if you start looking at the chemical composition and other characteristics, things like how they spin and a little bit about what shape they are, which is largely measured through things like spectroanalysis, telescopic spectral analysis, thermal analysis, like looking at these in the thermal wavelengths, radar studies, close enough ones they can hit them with radar and they can see what the shape of them is. And they fall into what are called families. So that's what is kind of shown here. The families often have they're often named, or they're typically named after the first object in that family. And subsequent research, which is really kind of an active area right now. In fact, there was a paper in Science just last week about this, suggests that families were originally one body and it got broken up by collisions and that sort of thing, which follows to reason. If you got a bunch of things that are kind of similar to one another, chances are they came from the same source, right? And so that provides some pretty big clues too about how the solar system came to be. It also kind of shows some of those things we kind of talked about earlier, right? If you look at this kind of busy diagram here, it shows you the size of the orbit. This is its AU, size of the AU, which you can again also kind of think about as distance away, right? How far it is from the sun. And then the top one is the tilt of the orbit, right? So some are inclined more than others. And if you kind of graph out the locations of a bunch of these things, they start falling into these families. This one right here, the Coronis family right here, a lot of meteorites that are recovered were pieces of a Coronis family object. But you kind of begin to see this structure again, where chemical composition changes with distance, right? The inner main belt is composed more of the irons and the stonies, and as you move outward, you start getting more and more of the more carbonaceous type. So there's this division there.
Is there a theory or?
Yes,
Official identification?
and it probably just has to do with density of stuff, right? As the denser stuff just collects more toward the center, and interaction with solar radiation probably plays a role in that too. But yeah, there's definitely, in fact, one of the things that I was originally going to talk about was that there's this gradient of composition of materials, and you see it reflected in the planets as well, right? The terrestrial type planets, the stony planets, are all close to the sun, and the gaseous ones further away. And the composition of the stuff that surrounds them kind of reflects that as well. But it's not a perfect representation of the primordial way that the solar system is, and that actually follows from kind of how the solar system came to be, right? So this is, obviously trying to pack a whole lot of information into one cartoon, but essentially at one point, for about 4.6 billion years ago, and that's a pretty solid date at this point. It's supported by a lot of different lines of evidence. Lunar rocks support this date, recovered meteorite material, even things like cosmic dust, stuff they've been collecting in the upper atmosphere, this dust kind of filtering in, all kind of converge on this. So this is probably a pretty accurate date. So about then, there was this kind of wispy cloud of gas and dust out there, probably composed of what we now think of as chondrules, those little tiny particles of stuff, basically. They started to coalesce, right? Probably what might have happened, this is probably, I think, at least as of the last time I really looked hard at this was the least well understood part of the process, but it could have happened that a shock wave of some kind passed through this cloud, like a supernova shock wave or something like that, started compressing it together, right? And so some places got compressed a little bit more than others. Those more compressed places began to have a little more gravity than their surroundings, which meant they started to attract more objects, and as things got larger and larger, its gravitational pull got greater and greater and greater, and so you started to get formation of clumps of stuff. The biggest one of those clumps became the sun. It got dense enough to actually start having nuclear processes, and it became the sun. And then all that other stuff out there, so we started getting nuclear fusion, right? Remember, this is mostly made out of mostly hydrogen, which is mostly what the universe is made out of. And so you squeeze hydrogen together hard enough and hot enough, and it forms helium and gives out a lot of energy, and that's basically what the sun does. But all that leftover material out there was probably in a kind of a circle, I guess you could say, a disk around the proto-sun. You can see these now. There are protoplanetary disks out there that are mostly measured in the kind of microwave part of the spectrum, but they look very much like what the primordial solar system probably looked like. It was differentiated according to material, right? The denser stuff was closer in, the more gaseous stuff was further out. But then something else must have happened, because you had the more solid material down to the center, you had the more icy stuff out there. By the time you get to the very far reaches of the solar system, it's all ices, right? And things like Trans-Neptunian objects and Kuiper Belt objects and all that are basically pieces of ice. And so comets kind of probably come from that area. But something else kind of had to have happened there. So this is kind of a graph that kind of summarizes all this, right? So if you think about this as distance from the sun, so we're going from about 1.5 AUs here up to about 5. The C types, and they're not perfectly segregated, right? The C types tend to peak a little further away. Those are the carbonaceous ones. The tendency for them to be primitive, to not differentiated. The S types and the N types closer in, but there's also this overlap here. So there's something else that must have happened here. By the way, the study of these, of the dynamics of these, has been an ongoing process for a very long period of time. Anybody know who Professor James Moriarty was? If you ever read Sherlock Holmes books, right? Professor Moriarty was the evil criminal genius in London, but
Yeah, anybody that deals with asteroids is that way.
Mhm. And his claim to fame in the day world, the non-criminal world, was he wrote this book on the dynamics of an asteroid, which it's pointed out in the books contains levels of pure math that are beyond the level of understanding of ordinary humans. But anyway, I always kind of like that characterization. Anyway. Probably, though, the dynamics of asteroids is probably a pretty interesting. In fact, the dynamics of the solar system is kind of an interesting story. And what it probably, the current thinking on it, there's two sort of interlinked models on this. There's the Nice model, and there's the Grand TAC model, and they sort of complement. As I understand it, they sort of complement each other. Although, as I understand it, there's also a lot of back and forthing between the Nice model people and the Grand TAC model people, which I occasionally catch glimpses of in some stuff I read. But, so essentially it was probably something like this, right? There was this accretion disk, this disk of stuff, right? And you probably had the harder, larger, more metallic things down here closer. Further out, you had other types of materials. But as you started getting coalescence in this, you started getting bigger and bigger objects. And the first things that probably formed were the gas giant planets. But they didn't stay where they formed. And this is really what kind of, it's thought, caused this current structure. And also one of the reasons why maybe the planet that's supposed to be where there isn't a planet, where the main belt is, never really had a chance to form. So the idea is that in the Grand TAC, as Jupiter and Saturn migrated inward, right, they migrated back outward, they tacked. I don't know if you ever sailed before, but in sailing they do this thing called tacking. It's a way of kind of moving against the wind, basically, right? So you use your sail like an airplane wing, basically. These planets do not have sails, but they kind of went back the other way. This is the part I don't understand, is what caused that to happen. I really have no idea. But that process of that Grand TAC, that inward and outward motion, mixed up the asteroid belt, right?
The
It
stability
stirred
of the sun has to do something about that.
Is it?
It may have been that in our early days, the sun was a lot more reactive
Mm-hmm.
and could have
Pushed.
I don't know, but that was one theory I read about.
I should probably look into that a little bit more, but
It's,
there's only so much time.
it's also speculated that one of the reasons why a lot of the exoplanets, you have the gases in close to their sun was a process like this, but
Mhm.
something happened in this solar system
To move it
that
back
caused
out.
them to go back out.
Yeah, the first exoplanet actually discovered was one like a gas giant, but really close to its star, like super close to its. It was a hot Jupiter. So yeah, that could have been like an example from an earlier time, basically, or what might have been similar to here.
Yeah,
Anyway,
which might suggest that what we see in our solar system is really the exception.
yeah, which maybe that's why we're here. It could be that in other types of structures there's no opportunity for life, that the conditions for life can't quite come together. Anyway, the result of all this stuff is that you end up with all the little rocky planets in close and all the big gas planets further out, or ice planets further out. And the asteroid belt, the area in between, is kind of a mixture of S's and C's and M's, but a semi-segregated mixture. So the GrandTAC kind of explains a lot of things. And one of the reasons why, if it's in fact an accurate picture, it kind of explains, goes a long way. Also explains why Mars is as small as it is. Mars should be bigger and Earth should be smaller. So that it's a great theory in the sense that it explains a very wide range of observations, which is kind of what makes a good theory. It's not necessarily a good theory and an accurate theory are not exactly the same thing, but there's evidence for this.
Well, and Earth and Mars at some point in time may have done a do-si-do,
Yeah.
you know, with mutual gravitation. They may have had a longer eccentricity
And at one time,
corrected itself.
you know, Earth might have collided with something about the size of Mars, and that's why we have a moon. You know, that's the leftover from that little
Yeah, which
encounter.
could have placed
Yeah.
Earth in a little different position.
Which the solar system was probably a much rougher neighborhood back in those days. But anyway, this is, I think, kind of a neat explanation for why we see this structure. There are actually other ideas out there. One of them has to do with chaotic motion. You know, chaos is this idea about how dynamical systems are really dependent on where they start, their initial conditions. So you end up with these quasi-stabilities, I guess you could say. And so there's a thought about that, and that actually points to other physical things that have been learned about how these small bodies work. So I thought this was kind of cool. This was from Sean Raymond at planetplanet.net. You know, site so nice they named it twice. But anyway, he says that the asteroid belt is a cosmic refugee camp. It's where everything ended up that got moved around when the planets tacked around and moved. There you can see Mars and Earth kind of doing a little bit of a dance. And so that's why we see the main belt where it is. It's this collecting ground that, you know, all that stuff that pushed out of the way when as the planets were kind of locating themselves. So that kind of is a bit about the main belt, which is of course where most of the asteroids are, but a lot of the interest that we have and humans are starting to develop isn't so much what's going on in the main belt, it's what's going on closer to home, and particularly near Earth objects defined as things that can essentially cross our orbit, basically. So this is a kind of a diagram of near Earth objects. One of the things I always love about these, you know, when you see the picture of the solar system in the textbook, and it's the sun, and then there's the planets, and they're all in a nice neat line, right? And then you look at what it really looks like out there, and it's this just chaotic, just wildly stirred up motion. So diagrams like this, I think, really do a nice job of getting that idea across. So near-Earth objects probably figure into the debate about what the actual events are, and probably it's a combination of these things. Something like the GrandTAC or the NEAS model probably actually happened, but chaotic motion is certainly also present. If you go out and look at the movement of some of these objects, you can actually calculate it. There's this thing you can calculate called a Lyapunov exponent that gives you some idea about the chaos of motion in something, and if you calculate those for asteroid bodies, you find that they lie in a range that would suggest that they are showing this chaotic motion, this kind of non-linearly predictive motion.
I will tell you that there's been about 3 or 4, I can't remember which, asteroids that got picked up and called comets because they had a tail. Well, that actually was a impact with another asteroid,
So it's leaving,
and it left the tail behind.
kind of leaving a stream of material.
Yeah, and so And so we do know that that interaction is taking place.
Well, and those collisions have to be
I've seen
fairly, they have to be fairly common, I would
Yeah.
think, yeah. I mean, you know, on an astronomical
I-
timescale.
I know you're talking about the distance between the asteroids, but there are over 1 million asteroids.
They-
So, you know, eventually, over a long period of time, you're gonna have some that get hit.
Yeah, so what likely maybe has happened here then, or again, the idea is that you've got stuff out here in the main belt that's moving around, right? Inevitably, they're gonna hit each other, right? Even in you know, it just has to happen. So you get these collisions, they break them up. That's probably part of the story of the formation of the families, right? These objects get broken up. They then start dispersing, and what disperses them is actually what's called a YORP or a Yarkovsky effect. I'll get to that here in just a second. But some of them are caught up in the gravitational train of the sun or the inner planets in such a way that they come head on in, and they become these near-Earth objects. So near-Earth objects were probably main belt, or at least parts of main belts at one time. This is probably also the source for a lot of meteorites. So a meteorite hitting the Earth is basically just a really, really tiny asteroid hitting the Earth, right? So there's a nice shot of a breaking up one. This is a collision, and you can kind of see that trail of stuff there, which again has been observed. What moves them apart is this YORP effect, or I can't remember who OR and P are. I can always remember Yarkovsky, but it's named after 3 people or 4 people. Yarkovsky being the senior one, I guess, because he's the Y. But anyway, the idea here is that if something emits thermal energy, that's kind of like a tiny little thrust, basically. So if one side of something is hotter than the other side and it's out in space, it exerts just a little bit of a force on it, and that can be over time enough to move it to a different orbit or move it out of its current path. So these YORP effects or Yarkovsky effects can kind of cause these things to move away from each other and maybe eventually towards Earth. There's several different families of Earth-crossing asteroids or near-Earth asteroids. They're mainly dependent on what their orbit looks like. So AMERs are the ones that are actually always further away than the Earth, right? They're always outside the Earth's orbit.
Yes. Yes.
But interior to Mars. So they're near Earth, but probably not quite the collision hazards that
Right.
some of the others
Yes.
are.
We have a more discovery that we've made.
Okay.
So
Yeah, I think it's the Apollos and the Aitons are the ones that are probably the more significant collision ones because they actually cross.
they are.
So Apollos are ones that have a semi-major axis larger than Earth, and Aitons it's smaller.
The Antares can also be a problem, but generally they are a little bit smaller. They're not quite as big.
Yeah.
So
And some of those little small ones that show up from time to time on the target lists, right?
Mhm.
Those
Yep.
really small ones, like maybe
Right.
only a couple meters,
right.
but moving extremely fast.
Yes.
Those are Atiras usually, right?
Well, no, they can be any of the 3. The Amoras probably not. The Amoras are out far enough away that they're not going to be fast movers.
Mhm.
But any of the other 3 can be a fast mover depending on what part of the orbit they're in and what our orbit is. So the closeness of any of those 3 is really dependent on that's where the speed comes from,
Mhm.
how fast they're moving.
Yeah, but anyway, these are all, the ones that actually cross the Earth's orbit are of increasingly intense. This is, again, one of the reasons why I think people are becoming more interested in studying these, is that these have not just the potential to hit Earth, but also have a history of hitting Earth. I think for a while there was some debate about whether or not some near-Earth objects were cometary origin or asteroidal organism. I think for the most part, the thinking is that they're asteroidal, although there are probably not burned out comets, but extinct comet. Would that be
There is a classification called the Damocloid, which has a comet-like orbit, but maybe not showing signs of leaving material behind.
Mhm.
So, even though, but it's got a very long orbit and very highly eccentric orbit, almost 0.95 or something in that range. So it's really,
So they must go way, way out there.
it goes out to the Oort cloud.
Yeah, wow.
Yeah.
But anyway, I think the thinking now is that most of the near Earths are former main belt objects, but there are probably some that are, I guess it would extinct comet be the right? It's comets that have kind of stopped acting like comets.
Right, well, they just have their all their volatiles
All the
kind of
volatiles.
burn off. It depends on how far out they go, because sometimes they'll go out far enough that they'll collect more material as they come back in. And of course, it's all frozen out there, so they'll keep that until the next pass. But, yeah, there's a lot of activity taking place.
Yeah, and it's a very dynamic place. So, what about these things? I mean, clearly they are a type of threat. There's big holes in the ground all over Earth that have been caused by objects of various sizes
And
hitting
there's
us.
many, many more that are hidden that you can't see anymore.
Yeah, there's one in Iowa that's completely eroded away, but it was a huge impact.
Nebraska's got one, it's a big one.
Yeah,
It's
yeah.
got a big
You know.
magnetometer reading around that.
Oh, really?
Yeah.
Where
Yeah.
is?
Where's that?
I think it's north and a little west of Lincoln, Nebraska.
Oh, is that guy? There was a guy from KU that thought he had found a
Yes.
Wakefield?
Yes,
Wakefield
yeah, I
Dorf?
think that's probably right.
Yeah, I know there was a lot of.
A geologist.
Yeah, do you know him?
No, I knew him.
Yeah, I heard him give a talk. I guess there was some doubt about
Yeah,
whether these
yeah,
will
there
really
was.
impact.
There was, but the magnetometer readings that he got was pretty convincing to me.
Yeah, I guess I didn't really feel like I had enough of a dog in that fight to really throw him an opinion out there. But what's clear is that there is potential danger from these.
Yeah.
The really huge ones, the ones that could be like extinction level events, pretty much know where they are right now.
Right.
And we also understand that, again, collectively we understand that they're really not a threat. The things that might be threats are ones that are much, much smaller, like this pretty big hole in the ground here, which, and if you've ever seen it, it's pretty impressive. It was probably made by, a building sized. It would easily fit on a football field. So that could be kind of a city killer. So there's a big emphasis now on understanding where those are. And that's the genesis of a lot of the work that Gary has been doing for years and years, and Parker and I have kind of chimed in a little bit on that, and Russ. So that's kind of the peril.
Mm-hmm.
The promise is that there could be economic value to these. I think this is a little fanciful. I don't ever really see, people going out and trying to mine these things in person, but you could do kind of automated mining of near Earth objects. We've actually sent probes, right? This was the OSIRIS REx probe, which kind of, I guess, landed on, made
Yeah.
contact with,
Yeah.
however you want to think about it, with
Yeah.
one of those rubble pile asteroids, and then returned a bit of it back to Earth. So we have pieces of this. When this got back, they had a hard time opening it. I think they were probably freaking out for a while because they couldn't get the lid off of the thing, basically. But eventually they did, which was good. And these, have some valuable stuff out there. There are metals in these that could be quite valuable and quite economically important if you could figure out an economically viable way to mine them, which some companies, including this one, Planetary Resources, are actively studying. I don't think there's really any plans right now.
I haven't heard a lot about.
I think the technology to do this is a long way
I
off.
think.
But,
so.
if you take the long view,
Yeah.
at least this is the thing that I just find astonishing, right? This is the potential value of some of these. So there's one called Davida, $27 quintillion, right? A quintillion is 10 to the 12th.
Now, there's a problem with that.
The entire
In that-
world economy is 175 trillion. That's 10 to the 9th.
In that, once you find these elements,
They're
then you, if you can dig them out and bring them back in,
then the
The
value.
price goes down.
They're not rare anymore, yeah.
They're
Yeah,
not as rare anymore.
yeah. It kind of reminds me, I don't know if you ever watched The Twilight Zone, you know, I used to love that show.
Mhm.
There was an episode where these guys rob a bank, rob a gold, they rob like Fort Knox and take all the gold, and then they go into like suspended hibernation for 100 years or so, and when they wake themselves up, everything is made of gold. So, you know, gold has become so common that it has no value anymore.
Rod Serling was a crazy guy.
Yeah, he was an interesting character. Anyway, so there's certainly promise here, but there's peril as well. And that's where we kind of have this Office of Planetary Defense, which, you know, if I could do it all over again, and I could figure out a way to work for the Office of Planetary
Planetary Defense.
Yeah, I would, just because it would be so cool to say I worked for the Office of Planetary Defense. And the first director, the person that actually established this, is a personal friend of right? You
Lindley, yeah.
yeah, went to school with him, is that correct?
Well, we were in 4-H together and Model Rocket Club
Yeah.
It's hard to imagine Lindley being in 4-H. I don't know.
Yeah.
It just doesn't.
and he grew up on a pig farm.
But anyway,
I know.
he was kind of the founder of this, and they're, you know, it's the Planetary Defense Coordination Office, and they're taking this whole idea of potential threat of rocks falling from the sky. It's very, very serious. Anybody get a chance to watch that little documentary movie that they made? I watched it over the weekend. It's a NASA thing, and he's featured very prominently, and it's about 90 minutes. Really good. Well, about the
That just came out here, what?
yeah, a couple weeks ago. Yeah, I watched it over the weekend. It was pretty good. This is actually a book that group put out, and it had this interesting quote in it where they're arguing now that asteroids and comets are not really astronomical objects anymore. They are environmental objects. They're now something we kind of have to worry a little bit, and we have to think of them as natural hazards and think about them from a cost-benefit basis, which is kind of a different way of thinking about it. This has led to the Asteroid Day, so every June 30th since about 2012 has been Asteroid Day. That's the anniversary, I believe, of the Tunguska event. So I don't know. I watched all the Asteroid Day stuff. It actually was headquartered in Luxembourg, but you know, they stream all these events. Very interesting. A couple of former U.S. astronauts, including one of the Apollo astronauts, Rusty Schweickart, pretty prominent in this organization that runs it. Of course, a little closer to home, you know, this is part of the
There's some
motivation.
weird characters.
I love this picture, you know, it's like, it just cracks me up every time I say it. We'll have to get one with Parker in it now too. So anyway, this is the motivation for the NEO follow-up work. It's all about establishing better information about the orbits of these things to know if they're potential threats or not. Of course, one of the things that we've done now is run a space probe into one of these to see if we can move it, which would be a way to, if you know about it far enough advance, you can nudge it just a tiny little bit, you can make it miss. Of course, you have to know very far in advance, so that's increases the importance of all this.
And it
kind of
made
stuff.
more of a difference than what they thought it.
Yeah, moved it.
It made about twice as much.
Yeah, I think it, you know, that would have just been great fun to build a probe just to smash it into something. I don't know if you've ever seen the little sequence of video of it approaching and approaching and approaching and approaching, and but yes. Anyway, so I thought I would just close with this guy. This is Brian May. You probably know him as the lead guitarist of Queen, the rock band Queen, but he also has a PhD in astrophysics, and he's kind of interested in these sorts of things. And he says, you know, we need to know if things are going to hit, and if Brian May says we need to know it, then by gosh, I think we need to know it. So anyway, that's it.
All right, very well.
So if you got any questions, I would be happy to defer them to Gary or somebody that knows the answers.
What's a magnetometer?
Magnetometer just measures the magnetism.
Measures magnetic field.
All it does is, and generally they go, I don't know, probably 5, 10 feet deep maybe, that they can pick something up. And they just go around in an area, and then if they find a ring, then they figure that was probably a steel meteor impact. By the way, the iron in iron meteorites is really high quality steel.
Yeah. They
The
were,
nickel and the iron in there are mixed in such a way that they make it. And that's the reason why they made swords out of them in the early days when they found the meteorite.
there was
Like
a,
stainless steel?
Yeah,
With all
kind of,
nickel in
yeah,
there?
right, with a lot of nickel and molly B and a few others.
there was kind of a famous meteorite that fell in southern Arizona called the Tucson Ring. And it actually looks like a ring, but they before they realized what it was, they used it for years as a blacksmith's handle. So they had this thing which would have, I mean, it must weigh God knows how much, tons. And they set it up in this blacksmith shop, and they were pounding away, and they couldn't damage it because the thing is just hard metal. And they finally
It's
figured
been
out.
forged with a pretty high temperature.
They finally figured out what it was, and now I believe now it's in the Smithsonian. But for quite a number of years, it was in some blacksmith in Tucson's shop. So. Okay. As always, if anybody wants to give a presentation, I'm always willing to.
I was gonna give that one, but you've done it already.
Okay. Well, I would have, if I'd have known that, I would have waited.
You might have been waiting a long
Would
time.
have turned the floor over. So I'm even going to contact name whose name is escaping me to see about an upcoming. What is it? I'm sorry. I blanked. Dave.
Cole.
Yeah, he's David Cole. He's given a presentation to us before, but I had what was he? Unfortunately, my memory doesn't extend that far back. But so I might contact him and see what the prospects are for.
Yeah, he had some medical issues with his wife had medical
Something
issues.
like that,
I don't know what it was, but it was.
He
Yeah.
was thinking possibly June.
Yeah. So I don't know. Maybe next month I might